Hello everyone, this is Stuart Mason back with Math 156 doing script 7a. We're talking about the surprising and useful appearance of the student's t-distribution. So the script opens with this little aside about the history behind the distribution. It's kind of interesting. So student is an alias of William Seeley Gossett, who I think was a chemist, but realized that he could do some statistical work to make his life easier working for Guinness Brewery. However, Guinness Brewery didn't want their competitors to know that they were using novel statistical methods, so he was forced to publish his results under an alias, and that's why we attribute the distribution today to student. And so Wikipedia has some nice background. Also looks like Paul's recommending an article here, and also that you go look up the original paper. The mathematics is, one, the terminology and notation isn't quite where it is today, and two, as the level of mathematics is just a step beyond what Paul requires for students taking this course, but still it's illuminating to take a look, and it's kind of cool to see some primary source history in action. But enough of that, and let's get our hands dirty with seeing how this distribution arises. So first, here's our sample. We're going to take two draws from a standard normal, store them in a vector called x. And x bar is the mean, s squared is the sample variance. In this case, it's rescaled to be unbiased, and you see x bar was surprisingly far from 0. The variance was pretty close to 1. Since we're only taking two samples, our estimators are not going to have a very tight range, so if we run this over and over again, we could get drastically different results. This time we got a mean a little closer to 0 and a variance a little further from 1. So now here Paul is going to explicitly compute the sample variance, it looks like. And then he's going to take what amounts to a chi-square with 2 degrees of freedom draw here. And then exploit an algebraic identity that we saw in the proofs. Another way of writing the same thing. Okay, so now we're going to draw two samples from a random normal 10,000 times and store all of these different examples in vectors. So it looks like keeping the means, the variance, squaring just the first sample, taking the sum of squares of both samples, and then performing this algebraic identity again. So let's see what we get. Okay, so our sample mean of all these sample means should be very close to 0. Our mean of all the sample variances should be very close to 1. And we know from properties of the normal distribution that the mean of the sampling distribution is normal with variance 1/2. And let's make this a little bigger on the right here. But sure enough, our stochastic data very nicely matches the theoretical distribution. Now square 1, which is just the square of the first sample, should be distributed chi-square with 1 degree of freedom because we have one squared normal variable, and sure enough, it is. Now the sample mean is centered at 0 with variance 1/2, so squaring twice it should give us something that also looks like a chi-square distribution, this time with degree of freedom 1. Although it looks like Paul didn't change that here. There you go. And the sum of both draws should be distributed chi-squared degree of freedom 2. Sure enough, it is. And we proved this earlier, that the sample variance and square of the sample mean are uncorrelated. And that's why this correlation coefficient comes back very, very close to 0. Not only are they uncorrelated, they're independent. By proving that they're not correlated, we didn't quite prove that they're independent, but I hope we might have convinced you that it's a plausible fact. Student did prove it, and you can see how it basically depends on a general form of the change of variables equations for multiple integrals, which we've been using in a very hand-wavy way every time we transform from Cartesian coordinates to polar coordinates, we always add that r factor. That's a special case of a more general way when you transform between coordinate systems. And so then Paul here convinces you that some of the other formulas we computed wind up being chi-square with degree of freedom 1. And now Paul is showing us how we can derive a sampling distribution for the mean without knowing the true variance using the sample variance. And the result is a student t-distribution with degree of freedom 1. Now note how very, very slim it is here around 0, and how fat the tails are, and also how long they go. Right? Usually when we graph a normal distribution, an r picks the axis for us. It stops around at most 3 standard deviations away from the mean, but here we're way, way far away from the mean. And Paul says that this is the student t-distribution with degree of freedom 1, and it's also the Cauchy distribution, which he cheekily calls infamous. The Cauchy distribution has an undefined expectation, and I think undefined moments of all variety. So its variance, skewness, kurtosis are all undefined because the integral blows up when you start multiplying by the value in question. Very interesting distribution. It's cool that such a simple distribution can have such pathological behavior. And sure enough, if we compute the sample mean and the sample variance, the mean we get something very close to 0, and the variance we get something wildly large. And if you look at the QQ plot, you'll see that far from 0, the distribution is highly non-normal. So now we can do the same thing, except we're adding 3 random normal variables. Our algebraic identity comes out to be 0. See, r is creaking under the pressure of how close we are to 0. Here's that value 2.2 times 10 to the negative 16 again. And this time we're getting chi-squares with 3 degree of freedom. We're still uncorrelated. We still understand the sample variance. And this time, if we construct our t-statistic and look at its distribution, it's a t-distribution with 2 degrees of freedom. I went a little too far there. Student t with 2 degrees of freedom, so we're a little taller in the middle and a little less fat in the tails. And our QQ plot is a little more normal in the middle, but still quite non-normal in the tails. Now let's set k equal to 10. The identity still holds up. So it looks like I went a little too fast before. We're not drawing from standard normal this time. We're drawing from normal with mean 3 and variance 4. So keep that in mind as we proceed. So our mean of the x bars came up very close to 3. Our mean of the sample variance squared came up very close to 4. And now we should get a chi-square with k degrees of freedom, in this case 10. And what I think is kind of cool, so we've seen ever-advancing degrees of freedom in chi-square distributions in this script so far, and you see that as we add more degrees of freedom, that's more random variables that we're adding together. Right? We start with basically one normal variable, square it, sum of 2 squared normals, sum of 3 squared normals, sum of 10 squared normals. As you add more random variables together, the result becomes more and more normal. So even though these are sort of transformations of normal variables, as we get more and more of them, this center creeps further to the right, and this skewness gets less and less severe. And the next thing you know, by central limit theorem, you can actually approximate high degree of freedom chi-square distributions with one simple normal distribution. So another almost layers within layers of the usefulness and surprising pervasiveness of the central limit theorem. And again, the correlation is 0. We can once again derive the student t-distribution. This time we expect 9 degrees of freedom. So in the numerator, we have standard normal random variable because we have subtracted our expectation and divided by our standard deviation. In the denominator, we have a chi-square random variable with 9 degrees of freedom. So we'll take the square root of that and take the quotient, and the result will be student t with k degrees of freedom. now the variance starts to behave. So Paul points out that if k is greater than 3, the variance is k minus 1 over k minus 3, and you can see how as k gets large, this will approach 1, which is what we expect, because this distribution should expect a standard normal distribution. And so the mean is behaving, it's very close to 0, and the variance is falling in a step as well. If we take the QQ plot, we see that we're much, much closer to normal, but still crazy things start to happen in the tails. Now we're going to take a look at what happens when we apply the thought process behind students' distribution to non-normal populations. So in the first case, we're looking at the uniform distribution, and the book has some nice illustrations of this. This is really just some hands-on examples of what the book is showing us. Basically, we're going to draw from standard uniform distribution, which theoretically has a expectation of a half and a standard deviation of the square root of 1 over 12. So everything else is the same except the underlying population from which we're drawing our samples. And it looks like we're still taking k equals 10 samples. So the algebraic identity always holds, regardless of population. And so these values are still going to be 0 or very near close to 0, as close as R can do it. And our estimator is unbiased, so the expectation is still close to a half, or mu. And the average of all of our sigma squares is pretty close to 1 over 12. Quite close, actually. However, the sum of squares is no longer a chi-square distribution, because chi-square distributions are sum of squared normals, sum of squared uniforms are something else. You see, they are, again, central limit theorem in action, close to normal, just not described by this chi-square distribution anymore. However, because the sample means are approaching normal thanks to the CLT, the resquared square of them should be close to a chi-square with degree of freedom 1, and in fact it is, because the CLT does apply. It would apply better with more samples, but as Paul pointed out 3 weeks ago, for distributions other than the normal distribution, the sample mean and sample variance are in fact correlated, and so this correlation coefficient will no longer be 0. Uncorrelated does not prove independence, but correlated proves non-independence. So we've thrown out the key assumption of the student's distribution right there by showing that these two things are not independent. Still, we can, as Paul says, studentize, and I just did air quotes around studentize, the random variable. And it's the exact same formula as before. So our numerator is the sample mean minus the expectation divided by the true standard deviation times the square root of the number of samples, and that's going to be this normal looking shape right here. And the denominator is the rescaled sample variance. I think this was W in our proof. And if we put them together in a t-distribution, yeah, we see that it's pretty good. And the mean and variance are well described. And the QQ norm is what we've come to expect by now, that it looks like a normal in the middle, but as we get through the tails, this approximation gets much worse. The book has some nice quantile plots of student T versus, in this case, the uniform, for example. I recommend taking a look at those as well, because they kind of illustrate how student T can go wrong when you're not drawing from a normal population. But the uniform distribution is symmetric, which means that we have not violated the assumptions of a t-distribution as egregiously as we could. So now we're going to use an exponential distribution, which you know is not symmetric and skewed to the right, and see what that does to the efficacy of our t-distribution. So once again, everything is similar to before. Now we have a theoretical value, expectation of 1, sigma of 1, and we're going to compute all the same statistics as before, except this time we're drawing from exponential lambda 1. The head is, so our 0 vector is still full of zeros, and our sample mean is centered around 1. Our sample means, plural, are centered around 1. And our sample variances are centered around 1. But the sum of our draws no longer is chi-square, because they're exponential, not normal. But thanks to the CLT, the reskilled square of the means is chi-squared degree of freedom 1. Again, that's because the sample distribution of means always approaches a normal. And the correlation is non-zero. We studentize it using the same formulas as before. You see our denominator is somewhat aberrant, and if we try to put together the student distribution, we get something that has a skew. So we have not enough weight on the right tail and too much weight in the left tail. And so this is sort of how the t-distribution can go wrong, although you see that it's not terrible, and as we added more and more samples, it would become better and better, thanks again to the central limit theorem. All right, so I hope this was helpful, and I'll see you guys back in a minute for 7b.